In the previous video, we introduced measures of association such as risk ratios and odds ratios. However, in real-world public health research, health outcomes are rarely influenced by just one factor. For example, blood pressure may be influenced by BMI, age, smoking status, physical activity, and many other variables. To analyze these relationships simultaneously, we use multiple linear regression. In this analysis, we are using the cardiovascular disease dataset from Kaggle to investigate what factors influence systolic blood pressure. Systolic blood pressure is represented in the dataset by the variable AP_HI, and this will be our dependent variable, meaning it is the outcome we want to explain. We will use multiple linear regression to examine whether factors such as age, body mass index, cholesterol levels, glucose levels, smoking, alcohol consumption, and physical activity are associated with higher or lower blood pressure. First, we install and load the packages needed for the analysis. We load Tidyverse for data manipulation and visualization, CAR for regression diagnostics such as variance inflation factor, and Performance for statistical checks of regression assumptions. Loading these packages ensures that all required functions are available for our analysis. Next, we import the cleaned dataset using the read_CSV function. This dataset has already been cleaned to remove impossible or unrealistic observations. After importing the data, we inspect it using functions such as head to view the first few rows and str to understand the structure of the dataset. This helps us verify that the data has been loaded correctly and that the variables have the expected format. Next, we check for missing values. We use colsums is .na to count the number of missing observations in each variable. Missing data can affect regression results and sometimes require additional cleaning or imputation. In this dataset, there are typically no missing values, which simplifies the analysis. Next, we compute summary statistics for the dataset using the summary function. This gives us information such as minimum values, maximum values, averages, and quartiles. These statistics help us understand the overall distribution of the variables and detect potential outliers or unrealistic values. So let's look at the summary of our dataset. AP_HI, which is systolic blood pressure, ranges from 80 to 240 millimeters of mercury. The median and first quartile are both 120. Which tells us that half of our participants have blood pressure around 120. The mean is slightly higher at 126.7, which suggests there are some high values pulling the average up. Age_years ranges from about 30 to 65 years, with a median around 54 and a mean of 53, indicating most participants are middle-aged. BMI ranges from about 10.7 to 60, with a median of 26.35. Most people are clustered around the mid-20s, but the high maximum indicates a few extreme values. These are potential outliers we might want to be aware of. Cholesterol and gluc are coded categorically. 1 is normal, 2 is above normal, and 3 is well above normal. Most participants are normal, but the mean is slightly above 1, showing some have higher levels. Smoke and alco are binary variables. Smoking is relatively low with a mean of 0.088, and alcohol use is even lower at 0.053. So only a small proportion of participants smoke or drink. Active indicates physical activity. Most participants are active with a mean of 0.8, meaning 80% report being physically active. Overall, this summary helps us see the typical participant profile, detect extreme values, and get a sense of which variables are mostly concentrated at certain values. Information that's crucial before we run our regression model. Before running a regression model, it is important to explore the relationships between variables. We first compute a correlation matrix. Correlation values range from -1 to 1 and indicate the strength and direction of linear relationships between variables. This helps us see whether predictors are related to the outcome variable or to each other. Now let's look at the results of our correlation matrix. This table shows how each variable is linearly related to every other variable. Remember, correlation values range from -1 to 1. 1 means a perfect positive relationship, -1 means a perfect negative relationship, and 0 means no linear relationship. Starting with our outcome AP_HI, systolic blood pressure, it has a moderate positive correlation with BMI 0.267 and age 0.209, meaning higher BMI and older age tend to be associated with higher blood pressure. Cholesterol also shows a smaller positive correlation, 0.195, with blood pressure. Glucose, smoking, alcohol, and activity have very weak correlations with blood pressure, suggesting minimal linear association in this dataset. Looking at the predictors themselves, cholesterol and glucose are somewhat correlated, 0.451, which makes sense because elevated cholesterol and glucose often occur together. Smoking and alcohol have a moderate positive correlation, 0.340, meaning people who smoke are somewhat more likely to drink alcohol. Most other correlations are very small, near 0, indicating that the predictors are mostly independent from each other. Overall, this correlation matrix tells us two important things. BMI, age, and cholesterol may be the strongest linear predictors of systolic blood pressure in this dataset. There doesn't appear to be problematic multicollinearity among most variables, except the cholesterol-glucose relationship, which we might keep an eye on. We then visualize some of the key variables, starting with the distribution of systolic blood pressure using a histogram. This allows us to see whether the outcome variable is approximately normally distributed or skewed. Here we are looking at a histogram showing the distribution of systolic blood pressure in our dataset. The x-axis represents systolic blood pressure measured in millimeters of mercury, while the y-axis shows the frequency or number of individuals within each blood pressure range. Most observations appear to cluster between roughly 110 and 140 millimeters of mercury, which is consistent with typical blood pressure values seen in adult populations. We can also see that the distribution is slightly right skewed, meaning there are fewer individuals with very high blood pressure, but those values extend into the higher range, approaching 180 to 200 millimeters of mercury. Visualizing the distribution of a variable is an important step in exploratory data analysis because it helps us understand the overall shape, central tendency, and potential outliers in the data. This information is useful before fitting statistical models since many modeling approaches assume that variables follow reasonably well-behaved distributions. We also create scatter plots between body mass index and systolic blood pressure. Scatter plots help us visually evaluate whether a linear relationship exists between predictors and the outcome. If the relationship appears roughly linear, it supports the use of linear regression. This scatter plot shows the relationship between body mass index and systolic blood pressure. Each point represents an individual in the dataset. The x-axis shows BMI, while the y-axis shows systolic blood pressure measured in millimeters of mercury. The red line represents the fitted linear regression line, which summarizes the overall trend in the data. We can observe a positive relationship, meaning that as BMI increases, systolic blood pressure tends to increase as well. However, the points are quite spread out around the regression line, indicating that while BMI is associated with blood pressure, Other factors such as age, lifestyle, genetics, and medical conditions also influence blood pressure levels. This type of visualization helps us explore potential associations before fitting more complex statistical models, such as the multiple linear regression model we will use to evaluate the independent effects of several predictors simultaneously. Next, we fit the multiple linear regression model using the LM function. Our model predicts systolic blood pressure using the following variables: age, BMI, cholesterol level, glucose level, smoking status, alcohol consumption, and physical activity. Multiple linear regression allows us to estimate the independent effect of each predictor while controlling for the others. The output of summary model provides important information, including regression coefficients, p-values, and the overall model fit measured by R squared. These results help us determine which variables are statistically associated with blood pressure. Let's walk through the results of our multiple linear regression model predicting systolic blood pressure. First, the model predicts AP underscore HI using 7 variables: age, BMI, cholesterol, glucose, smoking, alcohol use, and physical activity. Looking at the residuals, which are the differences between observed and predicted blood pressure, most values are close to zero, but there are a few large positive and negative residuals. This means that while the model works reasonably well for most participants, some individuals have blood pressure much higher or lower than predicted. Now, the coefficients tell us the estimated effect of each predictor, holding the others constant. The intercept is about 80, which represents the baseline blood pressure when all predictors are zero, though this isn't meaningful in practice. Age has a coefficient of 0.42, meaning each additional year is associated with about a 0.42 millimeters of mercury increase in blood pressure. BMI increases blood pressure by about 0.73 millimeters of mercury per unit, showing it's a strong predictor. Cholesterol is also positive with about a 3.26 millimeters of mercury increase per category. Smoking and alcohol use are associated with small but significant increases of 2.1 and 1.5 millimeters of mercury, respectively. Glucose has a very small negative effect, and physical activity is essentially zero, indicating no significant linear association in this dataset. The asterisks next to the coefficients show significance. 3 asterisks means highly significant, while no asterisk means not significant. Most variables except physical activity are statistically significant predictors of blood pressure. Finally, looking at overall model fit, the residual standard error is about 15.6, which tells us the average difference between observed and predicted blood pressure. The R squared is 0.123, meaning our model explains roughly 12% of the variability in systolic blood pressure. The F statistic is extremely significant, indicating that the model as a whole provides a better prediction than having no predictors at all. In short, this analysis shows that age, BMI, cholesterol, smoking, and alcohol use are important factors related to systolic blood pressure, but much of the variability is still influenced by factors not included in our dataset. This is typical for real-world health data. Next, we evaluate multicollinearity using the variance inflation factor, or VIF. Multicollinearity occurs when predictor variables are highly correlated with each other. High multicollinearity can make regression estimates unstable and difficult to interpret. As a rule of thumb, VIF values below 5 are generally acceptable. Values above 10 may indicate problematic multicollinearity. A VIF close to 1 means the variable is basically independent of the others. Looking at our model, age has a VIF of about 1.03, BMI is 1.04, cholesterol is 1.30, glucose is 1.26, smoking is 1.13, Alcohol is 1.13 and physical activity is 1.00. All of these values are very close to one, which tells us that our predictors are largely independent from each other. In simple terms, there's no evidence of problematic multicollinearity in this model. So each coefficient can be interpreted reliably as the effect of that variable while holding the others constant. We then generate the standard regression diagnostic plots using the plot function. These plots allow us to visually check several key assumptions of linear regression: linearity between predictors and the outcome, constant variance of residuals, normal distribution of residuals, and the presence of influential observations. Ensuring that these assumptions are reasonably satisfied improves the reliability of our model. Here we're looking at the 4 standard diagnostic plots used to evaluate a linear regression model, starting with the residuals versus fitted plot in the top left. This shows how the residuals are distributed across the predicted values. Ideally, we want a random horizontal band around 0. In this case, there's a slight curved pattern and widening spread, which suggests the model may be missing some nonlinear relationships and the variance may not be constant. Next, the QQ plot of residuals on the top right checks whether the residuals follow a normal distribution. If the points lie along the straight line, normality holds. Here we see noticeable deviation in the upper tail, meaning the residuals are right skewed and there may be outliers or heavy-tailed errors. Looking at the scale location plot on the bottom left, which assesses homoscedasticity, we want a flat trend. Instead, the red line slopes upward slightly, indicating increasing variance as fitted values grow. This again suggests heteroscedasticity, where the error variance is not constant. Finally, the residuals versus leverage plot on the bottom right helps identify influential observations. Most points have very low leverage, but a few observations appear labeled, meaning they may have relatively higher influence on the model. However, none appear to exceed the Cook's distance threshold dramatically, so extreme influence may be limited. Overall, these diagnostics suggest that while the model captures some structure in the data, there are signs of nonlinearity, non-normal residuals, and heteroscedasticity, which may indicate that model refinement, transformation, or a more flexible model could improve performance. Finally, we run formal diagnostic tests using the performance package. We check normality of residuals, which ensures that the errors follow an approximately normal distribution. The function check_normality model gives a formal test, and in this case, it issued a warning: non-normality of residuals detected, p less than 0.001. This means that the residuals deviate from a perfect normal distribution. In practical terms, this often happens in large health datasets like ours because blood pressure can have extreme values or skewed distributions. Should we panic? Not necessarily. Linear regression is fairly robust to small deviations from normality, especially with a large sample size like ours, over 68,000 observations. However, it's something to keep in mind. Extreme outliers could be influencing the model. In some cases, transformations of the outcome, like log or square root, might help improve normality. For inference, the large sample size helps ensure that p-values are still reasonably reliable. In short, the residuals aren't perfectly normal, but with such a large dataset, this is common and usually not a serious problem for interpretation of coefficients. Next, we check for heteroscedasticity, which occurs when the variance of residuals changes across levels of predicted values. The test also gave a warning: heteroscedasticity detected, p less than 0.001. This tells us that the spread of residuals is not perfectly even. In other words, the model tends to be less precise for some predicted values, often at higher or lower blood pressure levels. Like non-normality, This is common in large real-world health datasets. It can slightly affect the standard errors and p-values, meaning our confidence intervals might be a bit off. In practice, with a large dataset like ours, the regression coefficients themselves are usually reliable, but we should be cautious when interpreting statistical significance. So, both assumption checks, non-normality, and heteroscedasticity highlight that real-world data rarely fit perfect textbook assumptions, but the main relationships identified by our model are still meaningful. Later in the series, we'll dive deeper into how to handle these issues. We'll show how to transform variables like applying a log or square root to the outcome to improve normality and reduce heteroscedasticity. We'll also cover how to use robust standard errors or other techniques to make our statistical inference more reliable, even when the regression assumptions aren't perfectly met. This will help us make our model even stronger and more trustworthy while still interpreting the important relationships we've already discovered. In summary, our regression model predicts systolic blood pressure using age, BMI, cholesterol, glucose, smoking, alcohol, and physical activity. Age, BMI, cholesterol, smoking, and alcohol are positively associated with higher blood pressure, while glucose and physical activity show little effect. The model explains about 12% of the variability, which is typical in real-world health data. Multicollinearity is low, meaning each predictor's effect is independent, but residuals show slight non-normality and heteroscedasticity. In short, we've identified the main factors linked to higher blood pressure. And in upcoming videos, we'll explore transformations and robust methods to address these assumption issues and strengthen the model. In the next video, we will build on this concept and explore logistic regression, which is used when the outcome variable is binary, such as disease presence or absence. Continue the series as we develop more advanced modeling techniques for real-world public health data analysis using R